Sparks shower in orange constellations against the pre-dawn darkness of the fabrique. The legionary armor workshop, where a chunk of spongy iron the size of a man's fist bleeds molten slag with each blow. The metal hisses and screams. This is not the romantic forge of legend. This is violence made industrial, a battle against time, temperature, and the stubbornness of raw matter. In the next 12 hours, this crude mass will begin its transformation into the iconic overlapping plates of the Lorica Segmentata, the articulated iron cuirass that will guard a Roman soldier's torso from Caledonian blade and Parthian arrow alike. The journey from ore in the earth to armor on the legionary's chest is measured not in days, but in weeks of relentless labor. And it begins not in the forge, but in the suffocating darkness of a mine shaft, where men dig for iron with the certainty that the empire's frontiers depend on what they pull from the rock. The search for iron ore takes the Roman miner into veins of hematite and magnetite, often found in hillsides where the reddish-brown staining of surface rock betrays the wealth beneath. In regions like the Weald of Britain or the mountains of Noricum, the quality of ore varied enormously, and experienced miners could judge a deposit's worth by its weight, its color, and even the way it rang when struck. The excavation itself was brutal work, performed largely by slaves and condemned criminals under the supervision of skilled overseers. Tunnels barely wide enough for a man to crawl through were hacked into the earth using iron picks, with wooden props supporting the roof against collapse. Oil lamps flickered in the blackness, their flames consuming precious oxygen and filling the narrow passages with greasy smoke that coated lungs and skin alike. The ore was loaded into leather sacks and dragged or carried to the surface, where it was sorted by quality. Inferior rock was discarded on growing spoil heaps. The richest chunks were set aside for the smelters. Before the ore could be smelted, it required preparation. Workers crushed the raw stone using heavy hammers on flat anvil rocks, breaking it into pieces no larger than a walnut. This roasting process served a dual purpose. It drove off moisture and comete impurities while making the ore more porous and receptive to the reducing atmosphere of the furnace. The crushed ore was then spread on layers of wood and set alight, the flame slowly oxidizing the material over several hours. The smell was acrid, sulfurous, catching in the throat. When the roasting was complete, the ore had transformed from dense gray rock to a lighter, more friable substance that crumbled easily between the fingers. This prepared ore was now ready for the Bloomery. The Bloomery furnace itself was a deceptively simple structure, yet its operation required the accumulated knowledge of generations. Roman smelters in Britain and across the empire typically used shaft furnaces constructed from clay, rising 50 to 80 centimeters above ground level. The interior walls were thick enough to withstand temperatures exceeding 1200 degrees Celsius, and a small opening near the base allowed for the insertion of clay tuyères, the tubes through which bellows would force air into the combustion chamber. Building the furnace was itself a craft requiring days of work, as the clay had to be mixed with sand or crushed pottery to prevent cracking under thermal stress. The furnace was dried slowly over several days, then pre-fired with gentle heat before the first real smelt could begin. The smelting process commenced at dawn and would not end until well after nightfall. Charcoal produced in separate burning operations that consumed vast quantities of timber was loaded into the furnace first, filling the shaft nearly to the top. The charcoal was ignited, and teams of workers began operating the bellows, large leather bags attached to wooden frames that compressed and expanded in rhythmic alternation, driving a continuous stream of air through the tuyères. The roar of the fire was immense, a living beast consuming charcoal and exhaling waves of heat that forced workers to shield their faces. As the furnace reached operating temperature, prepared ore was added through the top in alternating layers with fresh charcoal, a handful at a time, at intervals of several minutes. The timing was critical. Add ore too quickly, and the temperature would drop. Add charcoal too fast, and the reducing atmosphere would become unstable. Inside the furnace, invisible to the smelters, but understood through centuries of empirical knowledge, a transformation was occurring. The carbon monoxide produced by the burning charcoal stripped oxygen atoms from the iron oxide ore in a process called reduction. At around 750 degrees Celsius, this reduction began. At 900 degrees, the iron entered its austenite phase, and carbon atoms began diffusing into the metal structure. The reduced iron, now in a semi-solid pasty state, slowly accumulated at the bottom of the furnace, forming a spongy mass called the bloom. Meanwhile, the silica and other impurities in the ore liquefied into slag, which pooled beneath and around the bloom. This slag had to be tapped periodically through a hole in the furnace wall, a dangerous operation that required workers to pierce the clay plug and allow the glowing liquid to run into prepared channels, the molten stream casting an orange glow across the workshop floor. The smelt might continue for 8 to 12 hours, the workers maintaining the bellows in shifts, their arms burning with exhaustion. When the smelters judged the bloom to be sufficiently formed, based on subtle cues like the color of the flames, the sound of the fire, and the behavior of the slag, the furnace was allowed to cool slightly. Then came the extraction. The breast wall of the furnace was broken open using iron bars, and the bloom, still glowing at perhaps 800 degrees, was pulled from the heart of the structure using long tongs. The bloom weighed anywhere from 2 to 10 kilograms, depending on the size of the furnace and the quality of the ore. It did not look like metal at all, but rather like a rough, porous stone, riddled with cavities and trapped slag. This was raw material, not finished product. The real work of the smith was only beginning. The bloom was transferred immediately to the anvil while still at working temperature. Here the smith began the laborious process called consolidation or compacting, hammering the bloom repeatedly to expel trapped slag and weld the iron particles together into a coherent mass. Each blow sent cascades of sparks and droplets of molten slag flying. The smell of burning metal filled the air, a sharp, almost sweet odor distinct from any other forge smell. The bloom was turned, rotated, folded back upon itself, and hammered again. The smith working with an assistant, who kept the bellows pumping at the secondary forge to maintain the metal at working temperature. This process might be repeated a dozen times or more, with the bloom returning to the fire between each session of hammering. Gradually, the spongy slag-filled mass transformed into a denser, more homogeneous bar of wrought iron. The quality of this iron determined everything that followed. Roman smiths recognized that iron from different sources possessed different properties, and they deliberately sought out specific ores for specific purposes. The ferrum noricum from the Alps was legendary for producing steel of exceptional hardness, suitable for weapon blades and cutting tools. For armor plates, however, the requirements were different. The iron needed to be tough and ductile, able to absorb impacts without shattering, yet hard enough to resist penetration. Achieving this balance required not just the right ore, but also careful control of the carbon content during forging. Too much carbon produced steel that was hard but brittle. Too little produced soft iron that would bend and deform. The smith worked by eye, by the color of the heated metal, by the way it moved under the hammer, adjusting technique constantly based on feedback that had no scientific name, but was understood through generations of practice. Once the bloom had been consolidated into a workable bar, the process of creating armor plates could begin. The bar was heated to a bright orange, roughly 900 degrees Celsius, and drawn out under the hammer, elongated and flattened with each stroke. The smith worked at an anvil, fitted with various hardy tools, stepped surfaces of different heights that allowed precise control of thickness. The sound of the hammering changed, as the metal thinned, from the deep ring of striking a thick mass to the higher, sharper note of shaping sheet. When the iron had been drawn to approximately the thickness of a man's finger, it was set aside to cool, then returned to the fire for further working. Creating the thin, uniform plates required for the Lorica Segmentata demanded exceptional skill. Each plate had to be between 1 and 1.5 millimeters thick, uniform across its entire surface, with edges that were straight and free of cracks. The earliest form of this armor, the corbridge type, consisted of 40 separate plates, 24 for the collar and shoulder units, and 16 for the girdle that protected the abdomen. Each plate had to be individually forged, measured, and finished. A single cuirass represented perhaps 300 hours of labor, from ore extraction to final assembly, not counting the work of the miners, charcoal burners, and ore roasters who supplied the raw materials. The shaping of the girdle plates was perhaps the most demanding operation. These horizontal bands wrapped around the wearer's torso in overlapping rows, each plate slightly curved to follow the body's contours. The smith began with a flat sheet and worked it over a curved mandrel, a shaped piece of iron or bronze mounted on the anvil, gradually hammering the metal into the required arc. The curvature had to be precise, too sharp, and the plates would bind against each other. Too gentle, and gaps would open through which a sword point could find flesh. The edges of each plate were then finished, either rolled under to prevent cutting the wearer, or the leather straps, or left flat with the corners carefully beveled to remove sharp points. The shoulder plates presented different challenges. These were not simply curved, but sculpted to follow the complex geometry of the human shoulder, allowing the arm to move freely while maintaining protective coverage. The smith raised these plates from flat sheet, using a combination of hammering over shaped stakes and careful planishing. The light, rapid blows that smoothed the surface and work hardened the metal. The articulated shoulder guards of the corbridge armor consisted of multiple small plates, riveted together through internal leather straps, each plate overlapping the one below to create a flexible defense that moved with the soldier's arm. The Newstead type, a later simplification, replaced these multiple small plates with larger single pieces, sacrificing some flexibility for easier manufacture. With the plates forged to shape, the drilling began. Each plate required multiple holes for the rivets that would attach it to the leather strapping system, and these holes had to be precisely positioned to ensure proper alignment when the armor was assembled. The smith marked the locations using a metal scribe, scratching lines into the surface that crossed at the intended drilling points. A center punch created a small divot to prevent the drill from wandering. The drilling itself was performed using a bow drill or pump drill, the rotating motion generated by the back and forth movement of a bow across a spindle wrapped with cord. The iron drill bit cut slowly through the plate, requiring frequent reversal to clear metal shavings and periodic quenching to prevent overheating. Each hole took several minutes to complete, and a single cuirass might require over 200 holes. The internal strapping system was equally critical to the armor's function. Strips of leather, typically vegetable-tanned cowhide, about 5 ounces in weight, were cut to precise dimensions and treated with neat's foot oil to maintain flexibility. These straps ran vertically on the inside of the girdle plates, connecting 3 or 4 plates each and allowing them to move in relation to one another as the wearer bent and twisted. The positioning of the rivet holes in the leather had to match exactly with those in the iron plates, requiring careful measurement and template use. When the leather straps absorbed moisture from sweat or rain, they would stretch slightly, a factor the armorer had to account for in the original construction. Assembly began with the girdle sections. The iron plates were laid face down on the workbench, and the leather straps were positioned over them, each hole carefully aligned. Copper alloy rivets, their heads already formed, were inserted from the outside of the plate, and the leather was pressed down over the shank. The protruding end of the rivet was then peened over a small anvil or bucking bar, flattening it against the leather to create a permanent fastening. The repetitive motion of setting rivets, the tap-tap-tap of light hammer blows, was the characteristic sound of the armorer's workshop. The shoulder sections were assembled separately, their more complex articulation requiring additional hardware. Bronze hinges connected the upper back plates to the collar unit, allowing the shoulder guards to rise and fall as the arm moved. These hinges were themselves products of skilled bronze casting and filing, their pins carefully fitted to allow smooth rotation without excessive play. The Newstead type later replaced these hinges with simpler riveted connections, and the belt fastenings that closed the armor at front and back evolved from elaborate bronze buckles to simple hooks, reflecting the Empire's constant pressure to reduce manufacturing time and cost. For armor destined for officers or elite units, additional decorative work transformed functional protection into statements of status. Partial tinning was one such technique, applying a thin layer of tin to selected areas of copper alloy fittings to create visual contrast between the silvery tin and the golden brass beneath. Recent experimental archaeology has revealed that this was achieved through a masking process, where areas intended to remain untinned were painted with egg white or egg glare, a refined form of beaten and settled egg white. This organic mask was then heated until it turned medium to dark brown, baking it onto the metal surface. When molten tin was wiped across the object, it adhered only to the exposed brass, leaving the masked areas untouched. After cooling, the egg glare was scrubbed away, revealing the contrast pattern. The technique required considerable skill, as Pliny notes that tinning in the Gallic provinces had become so sophisticated that plated items were almost indistinguishable from silver. Embossing offered another decorative option, with raised designs depicting military themes hammered into copper alloy plates from the reverse. These parade armor elements, sometimes called Paraderrüstung in scholarly literature, were long believed to be purely ceremonial, but recent analysis suggests many were functional battle equipment. The embossed designs were created by placing the metal sheet face down on a yielding surface, perhaps lead or pitch, and hammering from behind with shaped punches to raise the design. The work required absolute precision, as mistakes could not be corrected without leaving visible marks. The final assembly of the Lorica Segmentata brought together the collar unit, the two shoulder sections, and the front and back girdle halves. The front and back girdles were connected at the sides by loops and pins, or in earlier types, by buckles and straps. The shoulder sections were attached to the collar unit and draped over the girdle, with the lowest shoulder plates overlapping the uppermost girdle plates to prevent gaps in coverage. A properly fitted Lorica Segmentata conformed closely to the wearer's body, its weight distributed between shoulders and hips, its articulated construction allowing a full range of movement for marching, fighting, and all the physical demands of military life. The component parts moved in synchronization, a mechanical harmony that made the armor more than the sum of its plates. When the soldier raised his arm for a sword stroke, the shoulder lames slid upward. When he crouched behind his shield, the girdle plates compressed together. This flexibility came at the cost of complexity, as each moving junction represented a potential failure point. The hinges of the Corbridge type were particularly vulnerable, their small size and delicate construction prone to breakage under the stresses of combat and campaign. The evolution to the Newstead type, with its larger hinges and simplified construction, reflected lessons learned through decades of field use. The longevity of these armor types speaks to their effectiveness despite their complexity. The Calcrease type, the earliest known variant, remained in service for approximately 55 years. The Corbridge type endured for 70 years, and the Newstead type, the final evolution, served the legions for 90 years, before being gradually replaced by other armor forms. Throughout this period, the fabriques continued their work, the rhythm of hammer on anvil, the roar of forge fires, and the precise tap of rivet setting, marking the days and seasons of armorers' labor. The scale of production required to equip the Roman military machine was staggering. A single legion of 5,000 men needed thousands of cuirasses, each requiring hundreds of hours to manufacture, plus replacement parts for damaged armor, plus the tools and equipment for field repairs. The fabriques, the state-run manufacturing centers, employed hundreds of workers, organized into specialized teams: smelters, smiths, leather workers, bronze founders, finishers. Quality control was rigid, with inspectors checking each piece against standard patterns and rejecting any that failed to meet specification. The logistics of supplying raw materials, from the iron ore of distant mines, to the leather of provincial tanneries, to the tin of Britain and Iberia, represented one of the most sophisticated industrial supply chains of the ancient world. Yet for all this organization, the fundamental process remained what it had been for centuries: the transformation of rock into metal through fire and force, the shaping of that metal through skill and sweat, the assembly of shaped pieces into functional objects through patient, repetitive labor. The smelter judging his charge by the color of the flame, the smith reading the iron's temper by its glow, the armorer positioning his rivets by marks scratched with a scribe. All were inheritors of knowledge passed from master to apprentice across generations. No written manual captured the full complexity of their craft. The knowledge lived in hands that knew the right pressure, eyes that recognized the critical moment, and ears that heard the metal's message in the ring of the hammer. The Lorica Segmentata that emerged from this process was more than equipment. It was the tangible expression of an empire's industrial capacity, a standard issue item that represented an investment of labor and material beyond the reach of most ancient states. When the legionary marched to war in his articulated iron shell, he carried on his body the product of miner's darkness, smelter's fire, smith's strength, and armorer's precision. The armor would outlast him, passing to the next soldier in line, repaired and refitted for another campaign, another frontier. The fabriques would continue their work, the fires would burn, and the hammers would ring, until the legions themselves faded from history and the forges grew cold at last.